it's office hours and there aren't too many of you here. So what I'm going to do is I'm going to cover two questions on Airy stress functions. And one of them is going to be what we covered in class, and the other one's just going to be out of the textbook. And really for these two, I'm just going to focus on the boundary conditions, how to write the boundary conditions, because I'm guessing that's where you guys are stuck. Okay, when I did this in the class, this example in the class, we kind of did a couple of steps. First of all, I had given an Airy stress function. I checked if the biharmonic equation was matched up. And then I came up with the boundary conditions. By looking at each surface, I numbered them first and then decided or wrote down what the stresses should be for each of those surfaces. And then after that, I went off and worked out what the stresses were for this stress function by taking the derivatives based on the equations we had. Following this, I took the boundary conditions and I put them into the equations and solved for the constants. And that's how I found that all the constants were 0 except for C4. So what I'm going to do right now is just talk about the boundary conditions. So for this particular problem, the first thing I did, and the first thing you want to do, is look at what are the boundaries of your problem. So that's why I went off and named these boundaries, numbered them. So I called this 1, I called this 2, and I called this 3. And when I'm looking at a boundary, I'm looking at the entire boundary from top to bottom, from side to side, the whole boundary. So starting with boundary number 1. So what do we know about beams with pure bending, a cantilever beam with a pure bending moment? We know of the equation sigma xx is equal to my over I, right? So basically, we kind of know that with this kind of configuration, this being y and this being x, and a pure bending moment applied, I would have a sigma xx. That's it. So in other words, if I looked at surface number 1, and try to say, the stresses normal to the surface would be my sigma yy, and then I would have my sigma tau xy, right? Shear. These have got to be 0 because I only have a pure sigma xx coming out of a pure bending moment. So when I look at surface 1, then I'm going to pretty much say for surface 1, let's write down what the stresses are. And the stresses are, what is surface 1 first of all? Surface 1 is y is equal to the bottom, is the bottom surface. So it's y is equal to minus b over 2. And we said, the normal and the shear stress on this surface are going to be my tau xy, which because there's only a sigma xx is 0. A tau yy, a sigma yy, which ends up, there's no normal stress on this surface for a pure bending moment. Everything is sigma xx, so that's 0. I do the same for y is equal to plus b over 2. That's on my top surface that I just defined. So at b over 2, tau xy is 0, and any normal stress, which is my sigma yy in the y direction, is also equal to 0. So there's no sigma x on that surface, and so I only have those two, and those two are 0. Following this, I can start looking at the third surface, which is the interesting surface because the normal stress to that is my sigma xx, and we know it exists. Anything in terms of my tau xy, for example, does not exist because the pure bending moment only creates a sigma xx. So I can pretty much say that on that surface, now what is that surface? It's a surface that happens at x is equal to a, that entire surface. And I know for that surface that my tau xy is equal to 0, but my sigma xx actually has a value. How do I define that value? Well, I know that the sigma xx came about because of a pure bending moment. So how about I write the equivalent moment that that sigma xx creates? How do I do that? I take an integral. Because sigma xx is happening over the entire boundary, I have to integrate it from the bottom minus b over 2 to the top And I don't want to just integrate my stress, I want to integrate the force. To get the force, I need to take the stress, Newton per meter squared, and multiply it by a cross-sectional area. That cross-sectional area will be the length of this, since we're integrating, it will be the dy, right? If I integrate that dy, I'll get the length of that, and the thickness into the paper. So that would be my t. So now I have a force. I'm not done, because really my force is not what I want to equate my m naught to. I want to equate my m naught to a moment. So it's a force times a moment arm. And what is that moment arm? Well, the sigma is pointing outward this way, right? So the perpendicular distance is always going to be a y. So it will be a sigma y t dy that I will end up integrating. And once I do that, I basically have a force times a moment arm, which should equate to the external moment that was applied on it, because this is the external that was applied on it, and this is the equivalent internal moment that should match up. Now I wrote one more term, boundary condition, and that is a force boundary condition. So minus b over 2, if I integrate my force, which is sigma xx t dy, I should get the external force. But we do know that there's no external force applied, it's only an external moment. So this really needs to be, there's no F, it is equal to 0, because there's no external force applied. Now the t is really unimportant, because basically it's a constant. I can take it out of the integration, and I can divide it or remove it. So it is basically gone. I'm going to just take it out. So this was another boundary condition that I wrote out for this problem. So with these Airy stress function questions, you'll notice that there are, a finite number of possible combinations of loads and, beams, a cantilever beam with a end load, or a cantilever beam with a distributed load, plate with a varying load. There's just a number of them, and if you kind of just take a bunch of them and try to come up with the boundary conditions, that will help you. So example 2.3 in the text is a little bit like your question in your homework, question 2.3, I guess, the corresponding question. So it's kind of similar. So I'm going to go through the boundary conditions for this as well. So if you look at the boundary condition, if you wanted to do the boundary conditions here, first of all, notice that this is my y-axis and this is my x-axis. So let's make sure we know the direction of the x and y-axis is a little different from normal. And then we go off and do the same thing. We number each boundary so that we can write all the conditions that match them. So I would go off and say, well, this surface, let's call this boundary number 1. This one over here is boundary number 2. And then this surface over here is boundary number 3. So similar to what we did in the example in class, to write my boundary conditions for this, I would first of all start with the first one. Okay, so the first one is where y is equal to this distance, which is h. Y is equal to plus h, just because y is pointed downwards is positive, right? So y is equal to plus h. What kind of surface do I have over there? I'm looking at any stresses in this direction, and I don't have anything applied to it. So my sigma yy is equal to 0. Similarly, my tau xy is equal to 0 because there's no shear there. Now I can write that down. Sigma yy is equal to 0 and tau xy is equal to 0. I go off and look at the second boundary, and that's up here. Now I realize, well, for the second boundary, which is y is equal to minus h, I do have something applied, a Q, and this Q is per unit area, so it'll be newtons, let's say, per meter squared, millimeter squared, I don't know, but let's put something down that's similar. That's the same units as stress. So it's already been considered in terms of per unit area, much like stress. So in other words, if I think about, well, what is my sigma y on this? I would say, well, my sigma y is going to be equivalent to a q, right? And this q is minus q over there. For this surface, my normal is pointing upward, but my q is downward. So really my sigma y is minus q, right? The normal to that surface is pointing upward and my q is pointing downward, so they're opposing each other. There's a minus q over there. Or in this case, if you think y is positive, then you're really saying minus sigma y is equal to q, but either way works. So then you say, well, what about the shear on this? Similar thing, right? So if my shear I only have a q pointing downwards applied to it, there's no shear stress applied to that surface, so I can say tau xy is equal to 0 for that one. And then I go off to my third surface, and for the third surface, I mean, I can write tau xy is equal to 0. It might not help me as much as if I were to write the actual moment maybe equation. So if I were to write the moment equation here, well, there isn't a moment applied to this, but I can then use that to help me as a boundary. I can write force equations or moment equations to help me with the boundary. There is no force applied, there is no moment applied. So if I were to write at x is equal to 0, that's at this surface, what is my moment? Well, to get my moment, I would integrate, again, going from one end to the other. So minus h in this case to h. And then I take my sigma xx, because that would be what you would want to integrate, right? So the sigma xx, and convert that to a force because I want a moment. So force times a moment arm. To convert that to a moment arm, I have to take the sigma xx and multiply it by an area. That dA in this case would be the thickness times the dy. And that's my force. Integrating that force, I have to multiply by my moment arm. So the moment arm will be the perpendicular distance, which is in the y direction. So I would put a y here. In this case, the problem had it that it is a unit thickness. So t is equal to 1, right? The problem had a unit thickness. So I can pretty much say that this is equivalent to minus h over h sigma xxy dy, right? The t is equal to 1. And I know that since there's no moment applied, this is equal to 0. So just with these equations, and basically you have four kind of conditions here. You have y is equal to h, sigma y is 0, y is equal to minus h, sigma y is equal to minus q, that's 2. And then you have your tau xy, which is equal to 0 at plus and minus h, that's 3. And then you have another boundary condition here that you wrote up, and that's the moment boundary condition. And you really have four unknowns here. So four equations that come out of these boundary conditions can help you to solve for the four unknowns. And that's how it was done in the question. So I hope that helped. Again, if you have specific questions, you can email me. I'll respond to that as quickly as I can. And definitely come in for office